Can you guys hear me? I think, well, can you guys hear me? All right. Well, hi everybody. Again, thank you for inviting me for this conference. And in case people are wondering, I made a little bit of a mistake and I chopped the title of my presentation quite recently. So I won't be talking about relating the delta CKM with the delta PMNS. That has been done by Kiko yesterday. But I will be talking about this paper that I wrote with, well, Kiko, Gustavo, and Miguel Nebot last year. So this is sort of my line of attack. And let me just start with the introduction. So thankfully, we've had like a lot of presentations about multi-example models. So I'm going to assume that all of you at this point believe that these things are well motivated. However, they do have a problem, which is that at tree level, they have scalar-mediated flavor changing neutral couplings. And this is something that's very dangerous for things like K and anti-K missing. And it is for that reason that Glashow and Weinberg, a long time ago, introduced natural flavor conservation, which just completely killed them. Now, this was fine in if you're doing things like supersymmetry, where we have a lot of other things that can provide you with technology to do flavor physics. But if you want to do flavor physics with multi-example models, it turns out that natural flavor conservation ends up killing almost anything, and you don't have enough room to play. So you need something a little bit better. And the idea here is to find a framework where you can do flavor physics, but also be fine in terms of these kind of constraints. So let me just recall what the natural flavor conservation said. And the idea was that the mass matrix of a quark with a given charge can only receive contributions from one scalar. This is very well known. So motivated by some of our earlier work, we've decided to extend this idea with a new principle, which we call Trinity Principle. And it says the following. Each row of the mass matrix of a quark with a given charge can only receive contributions from one scalar, and vice versa. So what we're doing here is we're linking scalars with left-handed quarks and generations of left-handed quarks. The right-handed don't really matter. And I will tell you why in a second. Now, of course, you want to generate three massive quarks, so you're going to have at least three example models. And to test this idea, we'll look at the minimal models. And in order to avoid all of the issues with neutrinos, we're just going to focus on the quark sector. So, well, if you want to study the minimal models, let's first define what minimal models are. Also going to want to have at least the least amount of matter possible, so that's three example models. And we're also going to want to have the simplest symmetry. And because, like I mentioned before, the Trinity Principle doesn't care about the columns, you can just assume that all of the right-handed fermions are not transformed under this minimal version of the Trinity Principle. And what that tells you is that each row of the mass matrix is either going to be completely zero or completely arbitrary. Don't worry if you don't completely, if you can't see it at this moment, I'm going to show examples later. The point is that because scalar labels, they have no meaning, there's only three possibilities. Either all the scalars contribute to the same line in each of the mass matrix, or one of them contributes to the same in one and the other two flipped, or they're all completely flipped. Now, we've tested this, and I don't have the time to show you, but it turns out that the last one is not possible. The other two, however, are. So I'm going to start with the first one. So this is what I meant by the natural flavor conservation. You can see only one line per mass matrix per scalar, and it is obtained with two set 2s. The other one is with a set 3. This guy here to the cube is 1, and you can see that gamma 2 and delta 3 are flipped. Okay, so now that we have this Yukawas, it's time to look at the flavor change in neutral couplings and what have we done. So if you do a little bit of algebra, you'll find that these matrices ND and NU which are the things that control your flavor changing neutral couplings. They're written in a specific. Okay, so they're written in a specific basis. Not very important. What I want you guys to pay a lot of attention is to two things. First of all, and this is very important, we have here the mass matrix, and the mass matrix is completely isolated to the left. Now, this doesn't mean that we have natural paper constipation, because these here are 3x3 matrices. So when you diagonalize this guy, you not diagonalize these things. But if you look to stuff like, for example, K and anti-K mixing, because you have the DD here on the right, what's going to happen is that that thing is going to be controlled by the mass of the strange quark. So transitions between two quarks are controlled by the mass of the heaviest quark in that transition, and that is quite a powerful suppression. Well, in the natural multi-hexagonal model, you could say that they would be controlled by something of the top mass or something like that, which of course, the strange mass is much better. The other thing is that the path of the flavor is completely controlled by unitary matrices. And these are the ones that diagonalize the mass matrix. I will go to that in a little, I'll talk more about that later. So let's now look at the constraints. Now, because we only have quarks, the most stringent constraints are those that come from mass and mixing. And you can derive this sort of formula here. Now, this is, again, not very illustrative, because in reality, it's quite a big expression. What I want you to look at is that this thing here is, well, the coupling between the physical fermions and the physical quarks, and the physical scalar, sorry. So it involves the old guys and also the scalar mass matrix. Now, if you are okay with using some inequalities, you can find a condition which is much better, this one right here, which is sufficient but not necessary to ensure validity. So you could have models that don't satisfy this condition here, but are still okay experimentally. The important thing that I want you to pay attention to, though, is at this right-hand side here. So we have these ratios of couplings as to be smaller than 10 to the minus 1. But since all of the couplings that appear on this side are to the power of 2, okay, this means that our model requires only a cancellation of the order of 10 to the minus 2, which is much better than what you would find in a general multi-hexagonal model. So in sum, this Trinity principle does lead to models that are quite safe in terms of flavor. So now we're going to try to start doing something more. And the first thing we look at is at scalar potential. So these are the scalar potentials of the two models. I don't want you to pay too much attention for this. The important thing is that they are, both of them generate spontaneous CP violation. And why is this so important? Well, if you remember from yesterday, the talk by Kiko, there's a lot that you can do with spontaneous CP violation, assuming that you have the right type of flavor matrices. So, well, just one thing to tell you, in case you were wondering how many flavor parameters there are here, there are just 6. So the way to count it would be, for instance, you look at the down quark matrices. This is a 3x3 unitary matrix. It should have 9, but of course you can put 2 diagonals here with faces, so you leave 3 of them. And then in the up sector, the thing is just related by the CKM, which is already there in the standard model. So really, you're only adding 6 new flavor parameters. Now, the thing is this. So I illustrate you here just gamma 1 is in both models given like this, but you can see that in each model, each scalar contributes to just one line. So if you input CP in your Lagrangian, your color couplings are going to be real, which means that when you look at the mass matrix, all of the faces are going to come from the scalars. And because the scalars contribute in this way, your down quark mass matrix is going to be given by this expression, sorry, right here, where we have the faces to the left. And this is quite important because it means that the UD left is going to be given by this expression, which in turn means that CKM is given by this thing right here. And like Hiko have told you guys, this expression for CKM matrix is compatible with experiment. And what this means is that we can generate a complex CKM matrix totally out of the vacuum phases, which is something that's clearly not trivial. Of course, this is maybe for future work. Kiko also mentioned that if you do extend this kind of model to the lepton sector, you are then going to get relations between delta CKM and delta PMNS, and you're going to be able to play some flavor physics with that. I mean, in practice, it's a little bit more complicated, but that's kind of the gist of it. So this is kind of leads me to the end. So just finishing remarks, the main ideas that I want you to have is that, well, first of all, we've probed two distinct models which implement this Trinity Principle, both of them having naturally suppressed flavor-changing neutral couplings, both of them having potentials that generate simultaneous CP correlation, and both can produce a complex CKM matrix. So it seems as though the particular implementation of the Trinity Principle is not that important. The main thing is that it must satisfy Trinity Principle, and then at least if you, at this kind of level of analysis, they're kind of all the same. And the good thing is that definitely implementing the Trinity Principle generates flavor change and neutral couplings that are suppressed in a natural way, but has room to do flavor physics. And if you guys have any questions, I'll be happy to answer.
Thank you very much for.
Okay, there's already someone there.
So you have questions? So please.
There is no extra phases from Yukawa couplings, right?
No, the Lagrangian is completely CP
Of CKM naturally.
Yeah, the Lagrangian is completely CP invariant, so the Yukawas are linear.
Ah, okay.
Yeah, so all of the phases are from the scalars.
And how did you guess this?
Trinity Principle. Well, I'm working with Gustavo in the BGL models and stuff like that. And I mean, when I was working with them, I immediately thought that the important thing was the left one. And yeah, it can work quite well.
Thanks.
It's a kind of a BGL model.
Yeah.
So of course, you have a particular symmetry. You can play with different symmetries. You say flavor suppressed couplings. As far as I understand the BGL models, you have to make sure which coupling you put, because you might have different textures you can play with, and not all the structures give flavor suppressed couplings.
Okay.
So you have to make some selection, right? It's not so.
Well, so there's two types of suppression that play here. So the one with the BGL, which is quite amazing, is that you get the CKM matrix there. And in that case, yes, you do need to play to get the best. What I'm talking about here is, okay, I'm getting there. It's another type, which is, okay, I passed it. Yeah, so I'm talking about a different type of suppression that BGL models have, and these ones also have, which comes from here, right? So imagine that you're interested in doing like K and K and missing. Because this matrix is here, that thing is going to be suppressed by the square of the strange Yukawa. Now, in BGL models, you have more.
Let me say in another way. Is that I can make an arrangement? Is there any way that I can make an arrangement in such a way that you violate the flavor change of the recurrence? I believe there are other arrangements you do in this scenario, or at least in the BGL. I don't know for that.
I mean, I'm not sure if I can kind of understand your question.
I mean, maybe you asked value.
Actually, it's amazing. Some people have addressed this question, and it was, I think, done by Pedro Ferreira and João Silva. They have shown that if you think that, okay, BGL is just one particular realization, they have proved that these are the only realizations of multi-X model.
Yeah. So you can have. No. In this model you don't. Okay, so that's an important point. In this model you don't, because the labels have no meaning. So this is enough. Like this is all of them. Yeah, this.
Because in BGL there is a symmetry and here it's not, or
Yeah, this generalized BGL, it contains all of them. There is. It's here. Yeah, it's right here, the symmetry. Okay, so okay. Yeah, so here instead of in BGLs, instead of having this like unitary guys here, you have PCM. In these ones, you don't have PCM, you have this guy. But then everything else that BGL has, these ones also have. So this is like a natural way of generalizing BGL models. You lose a little bit of suppression, but you gain a little bit more room to do flavor physics. And in particular, like if you want CP violation, the power of the invariance that you need is quite lower here. So in these models, you only need like 4 couplings to get CP violation. There's like CP invariance, which is power 4.
Okay. So I think maybe it's time to stop discussion here.
Okay.
So another talk is by Pascal Anastasiopoulos. It is about string graviphotons, dark brain photons, holography, and the hypercharge portal.
So, first of all, I would like to thank the organizers for giving me the opportunity to present this work. The title is String Gravity Dark Photons, Holography and the Hypercharge Portal. It's a work in collaboration with Bianchi, Consoli, and Kiritsis, and in addition, I will present some ideas and some other works which are related, which are in collaboration with Begius, Mambrini, Niederweiser, and Oribe. So the plan of the talk goes as follows. I will give a motivation. I will describe the framework that I will talk about. In this framework, gravitons emerge. Also, this I will flash it. Also, gravity or dark photons emerge, and also, and here is the main part of my talk. But also, I will just flash again some discussion in this model, in this framework, where actions emerge and neutrinos emerge, and I will conclude. So, standard model is an effective field theory. In the infrared, we keep terms of this form. One part is made out of low-dimensional operators of standard model fields, and here this part is what we call couplings. These couplings, in general, could be dynamical. For example, the coupling to the stress energy tensor is the metric, which is dynamical and describes gravity. The QCD theta angle is believed to be dynamical and is related to the actions. In string theory, Yukawa couplings are also dynamical scalars, fuzzy moduli, etc. And in this talk, I will explore these couplings in a generic holography-inspired framework. So in this holography-inspired scenario that I will assume, all interactions in nature are described by 4-dimensional quantum field theories, and gravity, and there is no gravity. Okay, so in this framework, the fundamental theory consists of 3 parts. One is the standard model, and just a small set or sector of the fundamental theory. There is a hidden theory, which is arbitrary in general, is hidden in the infrared to the standard model, so there is no direct coupling between them, and a set of messengers. I will give soon more details on that, but this is the main framework. So from the standard model point of view, operators of the hidden sector will appear as fields, and some of them, which are protected by symmetries, will remain light in lower energies, and then they have particular interest for phenomenology. For example, the stress tensor of the hidden sector is an operator of the hidden sector. From the standard model point of view, after integrating out messages, so on, these people, graviton, the instanton density of the hidden sector, assuming that there is some abelian field living in the sector, and global conserved currents of the hidden sector behave like abelian gauge fields. Occasionally, so all these fields now remain light, and then we want to discuss their phenomenology. Occasionally, even heavy operators, which are not protected by symmetries, and they are heavy, they can give interesting phenomenology, like fermionic operators of the hidden sector or from the messenger sectors, which can play the role of right-handed neutrinos, and actually they can trigger the seesaw mechanism. So the big scale is good for this mechanism. Our goal in general is to beat the effective action of all these emergent fields and investigate phenomenological consequences. In various cases, we will assume that this hidden sector that I described before is holographic. The point is that all these fields, the graviton, the action, the gauge fields, the neutrinos, in this framework are composites, coming, as I say, the operators of the hidden sector, and they are very distinct from what has been considered so far. In this talk, I will just flash how gravitons, actions, and neutrinos emerge, but I will focus mainly in gravity and dark photons. So the picture actually that I described before is quite generic also in string theory. For example, this standard model, hidden sector and messengers between, is something that we face very oftenly in the brain constructions. For example, there is almost all standard model realizations, all the brain realizations of the standard model have this setup. So there is a set of D-brain stacks, which accommodate strings which describe the standard model particles. There are some hidden sectors of D-brains, which are there for stability and consistency of the total theory. And there are strings which are stretched between them, and usually they are massive, and their mass depend on the distance between the separation of these D-brains. So, and also in string theory, there is the closed string sector, which provides the graviton, graviphotons, Ramon actions, and so on. So let me give you some more details about the framework. So as I mentioned before, standard model, hidden sector, and messengers are the three sectors. The standard model contains all the known standard fields, quark, leptons, etc., Higgs gauge field. Sometimes we will loosen the standard definition by investigating extensions, and by that I mean that we will assume that there are some anomalous U1s, so which basically we can have in mind like Z primes, which belong in this sector. The hidden sector is a quantum field theory, which is ultraviolet complete. And so at the ultraviolet side, they are asymptotically free or conformal. The size is enormous, can be enormous, and the structure is random in general. But for sake of simplicity, we will assume just an SUN here. That's why this index here, N. And this N will be assumed to be large, even at astronomical values. So at weak couplings in the infrared, this hidden sector, we assume that contains all the simplest quantum field theories, vectors, scalars, and spin 1/2 particles. And this is motivated by the string analog that I mentioned in the previous transparency. The messenger sector, these messengers are fields which are charged under both standard model and the hidden sector. These are massive. In general, can be heavy or light. But in our case, we will assume to be heavy, and the scale we will denote with M capital. And this scale is the largest scale of all scales in this framework. So the picture is as follows. In the ultraviolet, this is the situation. But when we go below the messenger scale, the messenger mass, then we have to integrate out messengers. And what happens is that all gauge invariant operators of the hidden sector can couple to all gauge invariant operators of the standard model. Operators of the hidden sector, as I mentioned before, which are protected by symmetries, will remain light, and they are interesting for phenomenology. So more or less, this is what I just mentioned. Operators of the hidden sector are weakly coupled fields of the standard model. They are weakly because they are almost all these operators are irrelevant, and they are coupled by these kind of couplings. And operators which are protected by symmetries remain light. So in this framework, these people have worked out a case, and they have realized that the gravity is an avatar of a hidden quantum field theory. Assuming that there is a coupling between the stress tensor of the standard model and the stress tensor of the hidden sector of this form. Here is the T mu mu. Then this stress tensor of the hidden sector can play the role of the graviton. They have worked out in the far infrared the effective action of this example, and they have shown that the action is given by this form. So here you have a coupling of the stress tensor of the standard model with this emergent now graviton. They have a term which is related to the dark energy, and they have a cosmological constant which is given by this which are actually parameters of the hidden theory, and we have also the scalar and so on. This example here bypasses the Weinberg-Witten theorem because it has a non-trivial cosmological constant. This is at a linearized level. These people have worked out also the non-linearized level, at the non-linearized level, this model, and they have found out that this is a massive, in general, it's a massive graviton. And there's also a scalar. It's a very interesting model, I think. That even if it doesn't explain, even if this graviton is not the graviton that we know, it's a very interesting model that we can play with and make some phenomenology. Now, I want to focus on gravity and dark photons. So back to our framework. If we have some global exact U1 symmetries living in the hidden sector of this form, let's say, where these psi's are fermions of the hidden sector, then these kind of currents, they will appear like abelian gauge fields from the standard model point of view. These people have worked out the details of this, and they have found out that first of all, these U1s are very light, and also they have a compositeness scale where below that this field behaves like a point-like particle. However, above this scale, these fields start to have non-local kinetic terms, which is interesting also to study. They didn't go further, but it's interesting to study phenomenology and so on. Now, in our case, we want to study mixings between U1s from the standard model and U1s from the hidden sector, these global exact U1 symmetries. In general, we have three different kinds of symmetries in the standard model. U1 non-anomalous U1 gauge symmetries, the hypercharged. We might assume, as I say, extensions and say that, let's say we have a U1 anomaly, which is, let's say, Z prime, and we have non-abelian symmetries. On the other side, we can assume that we have global symmetries of the hidden sector where I mean, this is a classification basically where only messengers are charged, or kind of R-like symmetry where messengers and the hidden fields are charged, or flavor type of symmetries where only the large N fields are charged and not the messengers. In our case, we will focus in this example where we have U1s from the standard model and this kind of flavor symmetries. If we will work out the effective action for these fields, then in principle, these emergent gauge fields can couple to all invariant antisymmetric tensors of the standard model. So in general, at lowest level, sixth order, you can write these terms here. And here you can see that all of them are of the same form. So here is the field strength of the emergent gauge field. And here we have standard model fields. So these are standard model fields. This is the Higgs. This is the Higgs. These are fermions of the standard model, and so on. So the couplings are taken after imposing some effective field theory principles and large N expansions. And the point is that these emergent vectors here can play the role of gravity dark photons. They are weakly coupled to the standard model fields. And we having at hand an effective action of these dark photons with the standard model fields, we can try to study mixings with the standard model, with the abelian fields of the standard model, like the hypercharge, or an extension, as I say, Z prime, let's say, kind of fields, anomalous ones. Now, so having this, we can work out the Feynman rules and actually try to compute mixings. And we have done this in the broken and the unbroken phase. So in the broken phase, we can see that at leading order, we have this diagram that contributes to the mixing, and it comes from this and the minimal coupling of the Higgs to the hypercharge, or the Z prime, if we assume that there is one. And the contribution of this diagram comes at that. This is the coefficient in front, and this is the mixing. Next, at the next order, we have worked out the rest, and we have found the coefficients. Here I present just the coefficients, the red one, this part. At broken phase, we can work out also that. There also fermionic loops contribute at one loop. Here, but also we have a tree level, which comes from the expansion of the Higgs in the expectation value. Some comments, the contribution, all the contributions are due to the Higgs field, either direct, as I mentioned before, or via the Higgs-Engler-Brut mechanism. And because this comes from the mass to the fermions. Emergent vectors are expected to be light, as I mentioned in the beginning, and this can mediate a fifth force that even though none of the standard model particles are directly charged under it, it has these mixings and they generate effective charges. The couplings of the emergent vectors can be worked out, studying now the effective quantum effects from the standard model side, and we can see that it's given by these expressions here. So they go like 1/n square, and remember that n is very big, but also we have further suppressions because of this, and remember that this m capital is much larger than the scale of the standard model. Now, coming back to the string theory description that I mentioned before, this holographic inspired scenario is very similar to string theory picture. And in this ADS-CFT correspondence indicates that strongly coupled large N quantum field theories are dual to weakly coupled string theories, and vice versa. Weak from here, strong. Weak from here, strong from here. So in this framework, emergent vectors behave like gravity dark photons in string theory, and our goal is to compare couplings between these U1s and the standard model fields in the two scenarios. So in string theory, there are two classes of abelian gauge fields, either coming from the closed sector, never source sector, or Ramon sector, and these we will call gravity photons because they come from the closed sector where gravity is described in string theory. Or they can be open strings coming from the open sector, which are strings which are open strings which are attached on D branes with both ends on the same stack of branes, and this we will call dark brane photons. To compare the two models, we have first of all to do some string amplitude, to compute some string amplitudes. To do so, we have to for the closed and open strings that I mentioned before, we have to take different vertex operators. For close vertex operators have to be inserted in the bulk of the diagram. However, the open one on the boundary. And the standard model fields, we will assume that they are all open strings. That's the usual model building scenario in string theory. And so we will insert them in the on a boundary. The lowest surfaces are the disk, and so here we will insert on the graviphotons in the bulk or in the boundary, and the standard model fields on the boundary, as I mentioned before, or in the other boundary. And the reason why we don't put all together in the same boundary is because, as I mentioned before, this is a scenario that this is in the standard model is coming in a standard model debraying sector, and this is the hidden sector, and in between these are the messenger strings which are stretched between them. Sometimes we will also assume the presence of Ramon and never source fluxes. The reason is because, first of all, some technical part, we will normalize the vertex operators by assuming that all world sheet fields have length dimension. That's because we want the, actually I didn't write it, but the dx to be the same order of k psi psi in the vertex operators. We will use correlation functions in flat space, even though the dual picture is not flat. The dual picture in this ADCFT correspondence assumes that it should be a non-trivial asymptotically ADS gravitational background. However, for this comparison and at leading order, this is a good approximation. And to break this flatness, we will assume the presence of some Ramon and never source background fields. So this is what we have to do. This is the couplings from the standard model, from the effective field theory picture. Yeah, and these are the stringy amplitudes that we want to compute and compare. So here, for example, let's take this coupling. Here you have you have some standard model fields, which, as I mentioned before, we will insert their vertex operator on this boundary, and this is the emergent the graviphoton, which we will assume that this is coming from the closed sector. It will be inserted in the bulk. Similar for the rest. So here we have closed. Here we have the insertion of closed. These are the graviphotons here inserted, and in this list here, in this column here, we have the same like this, but with the presence of the flux, Ramon or never source fluxes. And finally, in this column here, I have is the diagrams which will contribute to these ones coming where this is an open string. And as I mentioned before, this should be inserted in the opposite boundary. So the results, we have several zeros, and some agree at that order. Comparing these two, you can see that we have agreement if the string scale, which we know is given by 1/n in the field theory side. And also we have this now 1/m square. It should be compared is given by this under this identification here. And so there is an agreement if we assume this. And we also assume that the Kaluza-Klein modes are analogous to the string scale, analogous to this M, the messenger scale. So this now it's with the insertion of the vertex operator, of the vertex operator of the Ramon or never source field. The results are all subleading. And the reason is that when we insert this, we have to normalize it by divided by the ms square. And finally, the same list of diagrams for the open case, for the open sector. These are results. Here, in that case, the m is played and is proportional to the distance of the branes, dx, delta x, over alpha prime. Again, these are subleading. So the summary of our results is that here on all the cycles have show the agreement, but all the rest are here. We have zeros at leading order, and the rest are subleading. The same results are expected even if we replace the hypercharge with the anomalous U1. And to see an effect of the anomalous U1, we have to go at 3 loop order, because there we would see something different. So the conclusion is that an anomalous U1 Z prime will couple to the dark photons the same way that the hypercharge does. So then U1s will weakly couple to the standard model field and can play a role of gravity photons, dark photons. When we are below, when we are above the compactification scale, then non-local kinetic terms appear, and then the effective action should be rebuilt. We have to study these cases. What happens is that the wave function spreads out, and it's different from the point-like case, and this will give new limits of the gravity photon, dark photons coupled to the standard model field. This we can even play a game and give some non-vanishing expectation values to the emergent U1s, and it's a very interesting option. This emergent U1 story is something that's not very much studied. Just to flash what I mentioned before, that in this framework we have actions which emerge, and the instable densities of the hidden sector play the role of behave like action-like particles. Again, they are very light, and they have a composite scale that above this they have non-local kinetic terms, and below they behave like the usual action-like particles. It's an interesting story to discuss, to study, and go on in phenomenological studies. Neutrinos, yeah, that's also a possibility to assume that neutrinos also emerge in this framework. And to conclude, we consider a holography-inspired scenario of the standard model and the hidden sector, which communicates via massive messengers. In this framework, operators of the standard of the hidden sector appear as weakly coupled particles to the standard model. Operators which are protected by symmetries behave like particles, and therefore they are interesting to be studied for phenomenological purposes. We focus on gravitons, actions, graviphotons, dark photons, and neutrinos. Phenomenological implications are on the go, and all these fields are very different from what has been considered so far. Thank you.
Session is open for discussion. Are there any questions of remotely? He's checking, so then please ask the question.
I'm confused with the emergent dark photons, for instance, and the framework, the string framework that you presented. What you call dark photons, open strings, gates fields, let's say, from the hidden sector.
From the hidden sector, yes.
And when you integrate all the messages, you find some effective description in terms of operators. Yes. What is the advantage of using the effective theory using operators, and you don't work directly with a string setup?
First of all, we wanted to compare, because due to ADS correspondence, we wanted to check, let's say, and compare the two models. In the beginning, the framework of field theory, where we have this, that all the world is made out of four-dimensional quantum field theories, is a framework that can stand by itself. So it doesn't need something.
I'm confused also with what you say, the ADS, the safety correspondence. Usually, when you do this duality, the gates theory is one dimensionless. So the field theory should be 4 dimensions. If the dual gravitational theory is 4 dimensional.
Yeah, all these are inspired by that. The reason we wanted to compare, so we wanted to compare the it's not one-to-one. We want to compare the couplings and what we get from string theory on one side, and because both are in the same limit at the end. And to see all these particles when we have the string theory and are described by these closed order strings, which look very much like the graviphotons that I described in the field theory picture. And we wanted to compare the couplings and to see if there are agreements or not.
Okay. So let it be the last question.
Yeah, comment first. Most of the participants here are more comfortable with an effective field theories, like in string theoretic framework, to do calculations and phenomenology. So your value of large, you say it's a very big N. That's my question now.
Yes.
So what is dictating that? Is dictating from because you like to match the dark photon mixing? Is that from the constraints comes, or is another theoretical constraint that comes from the hidden sector? Is that phenomenological the constraint, or is it just a theoretical constraint?
No, I would say it's a theoretical constraint. I mean, this framework has been studied by Nielsen from Nielsen very fast. So he assumed a hidden sector which was random and huge, and wanted to do something similar. So here, inspired by this holography, where n is big, we want to see if in such a framework without, I mean, the motivation was first to explain how, I mean, if gravity could be emergent and not, you know, the one that we know, and give a different interpretation of gravity. Yeah, later we try to see what kind of other emergent fields we can have.
Yeah, you know, in this. But your coupling F hat,
yes,
goes to one of the rank.
Yes, yes.
There are very strong couplings on that.
Exactly.
I don't know how heavy is your F hat.
No, the N is very big, and yeah, it's a very weak coupling.
Yeah, there is constraint, phenomenological constraint from that as well.
So I think it's time to thank you for the discussion. And now we can go to the last part of the session, which is remotely, and it is taught by Justin Abisher, and the title is Standard Model Predictions of the BC Lifetime.
Okay, thank you very much. And thank you very much for having me. It's a great pleasure to be able to give this talk. So I'm going to speak about the B sub C lifetime in the standard model. And let me start with a brief outline of my talk. So first, I'm going to give you a motivation, why we should look into this B sub C lifetime. Then I will show you the procedure that goes into this computation in the standard model. And then I will show you the setup that we use in our computation. And then we will see the uncertainties that come into the results, and then finally the results. And then I will briefly show you a new way on how to compute the B sub C lifetime in a standard model before I then summarize. And my talk is based on these two papers here, which were a collaboration with Ben Ginstein from UCSD. Okay, let me start with the motivation. So as we already heard today, there are several anomalies, mostly in the BT case. And here I will show you the ones that we've already seen from the charge currents. So RD and RD star, which are defined in this way. I will go a bit fast here because we have seen this plot already. So in the RD star plane, we have these several measurements, and the red one here is the combined one from Babar, LHCb, and Bell. And the black cross here is the standard model prediction, which is about 3 sigma away from the experimental value. So this is something interesting to look into. And the B sub C lifetime can come in here because it can constrain models that, for example, give a contribution which resolves this discrepancy. So one can constrain new physics scenarios from the lifetime of the B sub c. For example, one can look at the decay B sub c to tau nu and demand that this partial decay doesn't exceed the full decay rate or the full lifetime. And by looking at the branching ratio of this decay, one can, for example, constrain pseudoscalar scenarios quite severely. This was done in this paper here by Alonso, Ginstein, Kammerlich. And then one can also add other observables like the D star polarization or the tau polarization, which was done here, which constrains further scenarios, further new physics scenarios. So the new physics scenarios that are constrained here are, for example, 2 Higgs doublet models or scalar leptoquark models. Okay, so it's interesting to look into this tau BC. So let me give you a brief status on what we have. So the experimental value of the lifetime is about half a picosecond, which is quite well known from LHCb and CMS. And on the theory side, we can follow different routes. We can use an operator product expansion or OPE. We can employ QCD sum rules or potential models. And all these approaches here, they lead to kind of a number in the same ballpark around this number here. And I will mostly focus on this OPE approach here, and mainly on this paper here by Beneke and Buchala, which I'll abbreviate by BB for Beneke and Buchala. And in this paper here, which was done already in '96, these two authors, they found the lifetime to be 0.52 picoseconds. So very close to this experimental value here. Well, back then it wasn't measured, so it was a prediction, but with a rather large uncertainty here between 0.4 and 0.7 picoseconds. So this was one of the motivations to do a bit more precise computation of this lifetime. And so let me tell you what went into this computation here from Beneke and Buchala. So they assumed the B quark and the C quark in the on-shell scheme, whereas in our approach, we will use other mass schemes. And to obtain this error estimate, this rather large uncertainty, they varied the C quark mass within this rather large range, and then fixed the B quark mass such that the B sub D lifetime comes out correctly. So this is also something that one can improve of, certainly. And then also the penguin contributions to the decay rate or to the lifetime were not included, and we wanted to include them also in our computation. Okay, so let me tell you about a procedure that was used by Beneke Buchala and that also we followed in our paper. So the computation relies on the EFT approach on these 3 pillars here. So the first one is the effective Hamiltonian. So you integrate out the heavy degrees of freedom of the standard model at the electroweak scale. And this fixes the Wilson coefficients appearing in the effective Hamiltonian. And then you can run down to a lower scale, in our case to the B scale or the C scale. And at this low scale, one can do an operator product expansion. And once one has this expansion, one can express the operators that appear in this OPE using non-relativistic QCD. So here's just a picture of what I said. So here's the energy scale, and here we have the electroweak scale. And below is a lower scale like the B quark scale or the C quark scale. We take the standard model and match it onto the effective Hamiltonian, which consists of local operators multiplied by their Wilson coefficients. Then we run down to the lower scale. and employ this OPE, this operator product expansion, and express everything in non-relativistic QCD degrees of freedom. So this is the way to go. And what we also use for the computation is the optical theorem, which relates the decay rate of a particle to its forward scattering divided by 2 times the mass, where here we have this transition operator. And this transition operator is given by the imaginary part of this T product of 2 insertions of the effective Hamiltonian that we have seen before, that you obtain from matching from the standard model. And in the OPE, one finds basically that this transition operator is given by a series of local operators. So one can expand this thing here in terms of 1 over the mass, and then one has this expansion and can truncate at some point. So let me show you how this series of operators looks like. So this transition operator for a given quark Q, for example, has a dimension 3 operator, then a dimension 5 operator, Q bar Q, G mu nu, dimension 6 operators, and then you can even go higher in this expansion if you want. And all these operators here, they have Wilson coefficients, which are not the same as the ones from the effective Hamiltonian, but they have to do with spectator quark decays, at least these 2 here, dimension 3 and dimension 5. And for dimension 6, we have so-called weak annihilation and Pauli interference. I will show you in a minute which graphs contribute to these Wilson coefficients here. So generally speaking, the transition operator for the B sub C can be split into 4 pieces. The one for the anti-B decays, the one for the C decays, which make up the B sub C, B bar C, and then the weak annihilation and Pauli interference terms. So let me go into a bit more detail about these 4 contributions. So the B decays or the anti-B decays that contribute to the B sub C decay can be, for example, B going to Cu S plus D, or to C bar C S plus D, or to the semileptonic, or semileptonic decays. Then for the C decays, very similar, we have hadronic decays and semileptonic decays. And then we have this weak annihilation and Pauli interference, which are 1-loop graphs. I'll show you examples for all of these in a minute. And therefore, they are enhanced by an extra factor of 16 pi squared. So they are, this is why these are also important in this decay. So let me show you an example for B decay. So this graph here would contribute to the B bar B operator. So this is a 2-loop graph with 2 insertions of the effective Hamiltonian. And since we only want the imaginary part, we can basically cut here. And this would then give B going to C, U, D. So this is the B decay that contributes. Then for the C decay, this is very similar. We have these 2-loop graphs. Here I show you one where I attach another gluon. So this operator would contribute to the dimension 5 operator, C bar C, G mu nu. And then we have the dimension 6 operators, which come from this weak annihilation graph, which is, as you see, only a 1-loop graph. So if you cut here, you only have 2 particles in the final state. That's why you gain this extra factor. And for the Pauli interference, only the direction of these arrows here will change. So it's just another insertion of the operators of the effective Hamiltonian. And this also contributes to the B sub C decay rate. Okay, let me come to the setup that we used. So we tried to improve over the old paper from Beneke-Buchala by using different mass schemes. So instead of the on-shell mass, we used the MS bar mass, the meson mass, and the upsilon mass scheme. I will tell you in a minute what I mean by these schemes. Then, since we are in NRQCD, we can use spin symmetry to relate the different matrix elements among each other. And in the old literature back then, there were some typos which were pointed out by these people here, Kena, Lenz, Rao. And for our computation, we used these results here. And as I mentioned in the beginning, we also include the penguin contributions in the computation. They're not very large, but it's very easy to include them also. So we just take them also into account. And last but not least, we use much better input values, much more precise. For example, alpha S and the decay constant of the B sub C, CKM parameters, MS bar masses, etc., which are nowadays much better known than back in '96. Okay, just a word on the mass schemes. So as I said, we use 3 different mass schemes. The first one is the MS bar scheme, where we express the on-shell mass of the B and the C quark just in terms of the MS bar masses, MB and MC. Whereas for the meson mass, the B quark mass is expressed in terms of the upsilon mass, whereas the C quark mass is given in terms of the B quark and the spin averaged B and D masses. So here we just use an HQT relation, which relates all these masses together. And for the upsilon mass scheme, this is very similar to the meson scheme. And the only difference is that for C decays, we use for the C quark mass, not this relation here, but we use the J psi mass, very similar to the upsilon mass for the B quark. Okay, now let me say a few words about the uncertainties. So we do a non-perturbative expansion using this NRQCD. So this is a velocity expansion. So obviously you can go always to a higher order in velocity, and this introduces some uncertainty in the computation. Then we certainly also have a scale uncertainty, which is reflected in the mu dependence of the result. This can be cured by going to higher orders in alpha S. Then we have some parametric uncertainties, for instance, from VCB and also from other parameters which have some uncertainty. And if you neglect the strange quark mass in the CD case, then this will also introduce some uncertainty into the game. Okay, so let me finally come to the results. So here in this upper box, I show the computation for massless strange quarks, and the lower one contains the results for massive strange quarks. And for both, we have these 3 schemes here, the MS bar, the meson, and the upsilon. And we find in the MS bar scheme 1.58 inverse picoseconds, then for the meson 1.77, and here 2.5 inverse picoseconds. And if you assume the strange quark to be massive, then these get reduced by about 7 or 8%. So you find 1.5, 1.7, and 2.4 inverse picoseconds, which should be compared to the experimental value, which is 1.96 inverse picoseconds. And the main uncertainties here are from this mu dependence, so the scale dependence. This is really the dominant one. Then we have non-perturbative corrections, this velocity expansion. Then in the MS bar, we have some uncertainty due to the MS bar masses. And here also due to the non-zero strange quark mass and due to VCB. And if you add up all these uncertainties here, then you find that these three results in these 3 schemes are actually compatible with each other and also with the experiment. But obviously there's still, there's quite a large range of these among these 3 values. So there's certainly still room to improve. And what can be done to improve these results, to shrink the uncertainties? As I mentioned already, one can always go higher in alpha S to reduce the mu dependence, because this is the dominant uncertainty. Then one can go higher in the non-perturbative expansion, in the velocity counting. Or for the matrix elements that appear, it would certainly be nice to have some lattice calculation, lattice results for these. But this is at the moment not the dominant uncertainty, but this would certainly be something nice to have. Okay, now let me briefly discuss a new way to compute this decay rate, or the decay rate, which we presented here in this paper. So if you have a general heavy meson with a heavy quark Q, then you can write its decay rate as a sum of different decay rates. The first one is due to the free quark decay. So this has to do with the quark decaying. Then the non-perturbative corrections and the weak annihilation and Paul interference corrections or contributions. And then you can go higher in the expansion. And now this is not only true for the B sub C, but also for the B meson and the D meson. So if you use this formula for the B and the D meson and add them and subtract the B sub C contribution, then this piece here, due to the free quark decay, will drop out, because from the B you have a B quark, from the D you have a C quark decaying, and from this one, as we've seen before, we have the B and the C. So this piece here will drop out when you take this difference, and you're left on the right-hand side with the non-perturbative pieces and the weak annihilation and Paul interference contributions. And these here I just showed you before, how these are computed. And you can employ the same strategy for the B and the D. And on the left-hand side, for instance, you could use the experimental values for the B and the D. And yeah, the advantage, as I already said, is that this piece here, the free quark decay piece, basically drops out. And with it also its uncertainty, so it's getting a bit more precise in principle. And yeah, this is the main idea. So this formula here can be used obviously for the charge. So B0, B plus and D plus, and B0 and D0. So 4 possibilities in total to apply this, this formula. And what we find here very briefly is for the 0, 0 and plus 0, we find 3.03 inverse picoseconds. And for the ones with the charged D meson, we find 3.33 inverse picoseconds, which are both quite above the experimental value of 1.96 picoseconds. And so there are several reasons why this can be the case. So first of all, maybe we just underestimated simply the uncertainties, which come again from next to leading order corrections, from non-perturbative corrections or parametric uncertainties, etc. There can be other things here. So this is certainly the simplest explanation. Then one possibility could be coming from the I graph. So this is a contribution in the lattice, which is not included in the lattice calculation for the matrix elements. So for these back parameters that go into this calculation, because this I graph is difficult to compute, so it hasn't been estimated yet. But soon there should be a paper coming out which estimates this I graph in the with HQT sum rules. So it would certainly be interesting to see how large this contribution could be. Another possibility would be a violation of quark-hadron duality. Then we would certainly find another way on how to compute these things, because this is really one of the keys to to do this computation. And then there's certainly also other possibilities, which I don't mention here. Okay, so let me already come to my summary. So I showed you the operator product expansion calculation for the B sub C, and the results are in quite good agreement with the experiment, but there's still some large scheme dependence, because in these 3 different schemes you get the different values. So improvements for this calculation would be higher order alpha-S corrections, higher order non-perturbative corrections, maybe some lattice results one day. And then I briefly showed you this novel way using these differences of decay rates. And there the discrepancy could be due to underestimation of the uncertainties, due to this I graph, or maybe due to duality violation. Okay, thank you very much.
Our presentation, so now session is open for discussion. Are there, so please? Very interesting talk, but I'm a little bit surprised by the large spread of predictions. I mean, the original range given by Benecke and Buchalla from 0.4 to 0.7, I think obviously was, you know, clearly is a bit outdated now, but still, especially this improved method, I mean, that the values are so far off. Do you have a feeling? I mean, maybe some of the schemes that you're looking at are not particularly case, or can one say this, whether the meson or the Upsilon scheme maybe is an expansion around unreasonable scale? I'm not sure what to make out of the numbers. I mean, the most pessimistic conclusion would be this is probably not very well controlled, this operator product expansion.
Yeah, that's right. Yeah. I mean, I would maybe tend to the Upsilon scheme, because in this scheme, we checked, for example, some semi-leptonic decays, and there we find quite good agreement with which was done in the literature, because this Upsilon scheme is supposed to converge much faster than, for example, the on-shell or the MS bar scheme. So this would be one thing, but obviously, as you say, I mean, it's already above the
technique, right, that seem to eliminate the dominant terms in the series, and then the subleading terms are so far off. I'm really a bit surprised.
Yeah, indeed. Yeah.
Other questions? Maybe remotely? Could you check? Okay. It seems that there are no any more questions, so we can close the session. Thank you very much for presentation.